Basically, it's a capital E and values of finite sums, Riemann sums, and limits of Riemann sums. So why you're studying this is numbers are used all the time, whether you notice them or not. Sequences are numbers separated by a comma, like 1, 2, 3, or 10, 20, 30. Series are numbers separated by a plus sign, like 1 plus 2 plus 3, or 10 plus 20 plus 30. Using sigma notation is a convenient way to work with sums that have a large number of terms. Sigma notation enables us to write a sum with many terms in a compact form. So, for example, on this one, we would just say the sum of, I don't know, I'm just making it up, 10i, saying I goes from 0 to 3. Actually, in this case, I need a 1. I equal 1 to 3. So that would mean 10 to the first plus 10 to the second plus 10 to the third. So 10 plus 20 plus 30. So that's what we would want for that one. So the Greek letter capital E, it's like capital sigma. Sometimes it corresponds to the capital letter S, stands for sum. The index of summation K tells us where it begins. So on my example, I put I. In some cases, they want K. It's the number below the symbol. And then there's also a number where it ends, which is at the top of the number. Any letter can be used to denote the index, but I, J, K, and N are the customary ones. So the symbol is used to denote a sum of multiple terms. The symbol generally has your index that encompasses all terms that have to be considered. The summation of an explicit sequence is the succession of additions, like adding several times in a row. So summation 1, 2, 4, 2 means 1 plus 2 plus 4 plus 2, which is 9. Summation is the addition of any sequence of any kind called add-ins or sum-ins. The result is their sum or total. Besides numbers, other values can be summed as well. Functions, vectors, matrices, polynomials, and in general, elements of any math object where they say plus is defined. Very often, elements are defined through a regular pattern as a function of their place in the sequence. For example, for simple patterns, summation of long sequences have ellipses, which are the 3 dots. So summation of the first 100 natural numbers, they put a few numbers, then they put ... then they continue it. Otherwise, summation is using in summation notation with the enlarged capital Greek letter sigma. And so it'd be E from I to N. So we would write that as I equal 1 to N. So this is your start, and this is your stop. For long summations and ones that are variable length, it's common to find closed form expressions. And then you have some formulas. This one's important for linear. It's n times n plus 1 divided by 2. And then you have another one for quadratic. That means for n squared. and that's n times n plus 1 times 2n plus 1 divided by 6. So you basically take the ending point, add 1 to the ending point, and then double it and add 1. Multiply those three numbers and divide by 6. And it's also called the first n squares. The formula for cubic, which is n cubed, would be n times n plus 1 over 2, all of that squared. And that's called the first n cubes. There is a sum rule where the sums can be split, and a difference rule where they can be split. There's a constant multiple rule. This kind of reminds me of limits when we, had different rules. There's also a constant rule where it's n times c. I guess that's it. Okay. So for this first one, it says write the sum without the sigma notation and then evaluate it. So if k is 1, then we're doing 12 times 1 over 1 plus 2. Now the way they did it is they had parentheses and they used the times sign. And that's your first term. So this is for k equal 1. Now we also need for k equal 2, and so we need plus 12 times 2 over 2 plus 2. Or, 12 times 2 over 2 plus 2. So that's actually your answer for the first, and then for this one, they want you to work it out. So that'd be 12 over 3, which is really 4. This would be 24 over 4, which is really 6, and we get 10. So that's how that works out. Now, on the next one, they want you to write it without sigma notation, and what you see is you're going from 5 to 9. So here's the 5, then you go 6, 7, 8, 9. Pretty straightforward. And then your answer is listed. Now, it's not always going to be 0, just being honest. Like if you had this many terms instead of that many terms, it could be different. So the best way is make sure you're in radian mode for this problem. And so I've got to do that there. And then you say sine 5 pi plus sine 6 pi plus sine 7 pi plus sine 8 pi. That's the best one. Plus, whoops, I needed a plus. Plus sine of 9 pi. And it's still 0. So you may wonder, well, why is that? Well, let's relate it back to trig. This is the ordered pair negative 1, 0. And remember, if it's x and y, this is cosine sine. And so what they're saying is do sine of looping around 5 times, which is really 0, plus loop around 1 more time, it's still 0, and so forth. And so that gives you 0. Now, of course, in your example, you might have cosine, you might have something else. It might be pi halves, 3 pi halves, so forth. So just be careful. Remember, when we loop around, it's like 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. Oh, okay, so these evens are going to be 1 comma 0. And again, sign is y. So you'd have this 0 from 5 pi plus this 0 from 6 pi and this 0 from 7 pi, this 0 from 8 pi, and this 0 from 9 pi. And so you get 0. Okay, now moving on to number 3. It says to write it without using the notation. And so basically, if your k is 1, then you have a 1 exponent. And so they literally want you to put, that. You have a 1 here and a 1 there. This time you have a 2 there and a 2 there, and a 3 there and a 3 there. So that's what you'd get. Now, to evaluate it, let's just type it in the calculator. If it's only a few terms, I'd probably just do it that way. You know what? I'm going to try to be fancy. Okay, so I did it once and I got -1. Now I'm going to do it and I'm going to change this to 2 and this to 2, and I get -1. And then the next one's also -1, and so you get -3. Now I could have done this plus this one plus this and change this to 3 and change this to 3. Oops. And so then I get my -3. So that's how you do that. Now you have ones where you got to figure out if this is right for these formulas. And so for part A, okay, and this is going from 1 to 5 for part A. For part B, it's going 0 to 4, and this is -1 to 3. And then you have different exponents. And so you can't just assume it's always all 3. But for the first one, k equal 1 to 5, 4k minus 1. Well, that means 4 to the 1 minus 1. So 4 to the 0 is really 1. Okay, so that's our first one. And then for the second one, we have 4 to the 2 minus 1. So that means 4 to the first, whoops, that should have gone up here, which is just 4. And then 4 to the 3 minus 1 means 4 squared, which is 16. And so then, it's going to follow that pattern. So that did work for the first one. Now for B, this time we're going the sum from k equals 0 to 4 of 4k. So that'd be 4 to the 0, which is 1. Remember, any number to the 0 power is 1, plus 4 to the first, which is 4, plus 4 squared, which is 16, and so on. So that one worked also, in my case. Now the next one, they have a -1 there. And so the sum from k equal -1 to 3, 4k plus 1, means you're doing 4 to the -1 plus 1, which is really 4 to the 0, which is 1. And then you're going to say 4 to the first. Let's see. Because that's 0 plus 1. It's 4 to the first, so you get 4. Then for the next one, you do 4 to the 1 plus 1, so we say 4 squared, which is 16. And so those are continuing. And so in my case, it was all 3. Now, before you get too excited about that, look at this one right here. It wasn't all 3. So be careful. So on this one, we're trying to match this pattern with alternating signs. And so we have the sum k equal 1 to 6 of -3, k minus 1. So that means we have -3, and then we do 1 minus 1. So that's really -3, 0, which is 1. So there's your first. Now when we put in a 2, it's -3, 2 minus 1, which is really -3 to the first, which is really -3. And then you have -3 to the 3 minus 1, which is -3 squared. Remember, use your parentheses, and you do get +9. So that's why that one works. So that's A. On B, we have the sum k equals 0 to 5, -1 to the k, and 3 to the k. All right, so on this one we have -1 to the 0 times 3 to the 0. Well, that's just 1 times 1, which is 1. Then the next one, this is -1 to the first, 3 to the first. And so that's -1 times 3, which is -3. Now we have -1 squared and 3 squared. So that's going to be +1 times 9, which is +9. And then let's continue. -1 to the third, 3 to the third. So that's -1 times 27, which is -27. So that did continue. I did a few more since it's alternating signs. I just wanted to make sure, and it worked. So now for C, we're doing the sum k equal -2 to 3 of -1, k plus 1, 3, k plus 2. So that's -1, -2 plus 1, which is really -1, -1. Remember, the negative exponent in this case means it's 1 over that number, and so we get -1. So that's a bad starting point. We needed +1, not negative. We needed 1, not -1. And if we test another one, oh, I didn't even do the back part yet. Okay. 3 to the -2 plus 2, that's 3 to the 0, which is 1, and so we get -1. Okay, so that's for the first term, which was incorrect. And if we do the next one, it'd be -1 to the -1 plus 1. So that's -1 to the 0, which is really 1, times 3 to the, let's see, 1 plus 2. So that's 3 to the third, which is 27. Okay, so this totally is wrong. If you get 2 of them wrong, like, you're pretty confident it's not going to work. So this one did not work for me. Now on this one, they say which one is not equivalent. So if you're like cutting to the chase, you're going ahead, you're going to say this is yes, this is yes, this is no. It is not equivalent. Okay, so let's actually do the work. So if we have the sum k equals 6 to 8 of negative 1 k minus 5 over k minus 5, that's going to be negative 1 to the 6 minus 5 over 6 minus 5. So that's negative 1 to the first over 1, which is negative 1. Okay, so that's for the 6. Now for the 7, we'd say negative 1 to the 7 minus 5 over 7 minus 5. So that'd be negative 1 squared over 2, which is a half. So our sequence starts with negative 1 plus a half. Okay, there's 2 terms. Let's check this one. So we're going from negative 5 to negative 3. So if we do the sum from k equal negative 5 to negative 3 of negative 1 to the k, k plus 6, then this is negative 1 to the negative 5 power over negative 5 plus 6. Remember, when it's a negative number to an odd, then it's going to be negative. So negative 1 over 1 is 1. So right here, I just got distracted. Negative 1 over 1 is definitely negative 1. And so that pattern matched for the first term. Now for our next term, we want negative 1 to the negative 4 power over negative 4 plus 6. Now when you're doing an even number like that, that's just going to end up being positive and then a 2. And so there's your half. So those two matched. Now, I'm going to call this A, B, and C. So this was A, this was B, and here's C. So for this one, we're doing the sum from k equals 0 to 2, negative 1 to the k over k plus 1. So for the 0, it's negative 1 to the 0 power over 0 plus 1. Negative 1 to the 0 power, or anything to the 0 power, is 1. And so I get 1 over positive 1, which is 1. So right there, there's a problem. The first two went to negative 1. This one went to positive 1. And so this does not match. Let's do one more term. So if we do negative 1 to the first power over 1 plus 1, that'd be negative 1 over 2. So it looks like there's just a sign problem, so that one does not match. So they would need like a negative sign out in front for it to match, or some other thing. Okay, Now for this one, there's not much work for number 7. Basically, it says express it in sigma notation. They started the k equal 1. So all you do is you put that number right there, and then you put the k right here. So that's basically it. It's the linear one. Well, I mean, it's the constant rule. This is the constant rule. Okay, now on this one, you can see there's 4 terms, and so you put a 4 there. And then, let's see, this would be like 1 to the 4th is 1, 2 to the 4th is 16 because that's like 4 times 4. 3 to the 4th is 81 because it's 9 times 9. And 4 to the 4th is 256 because that's like 16 times 16. And so you'd have to recognize whether your number is to the 3rd power, the 4th power, or the 5th power. In my case, it was the 4th power. And so it's k to the 4th. Now on this one, again, we have 4 terms, so the little 4 goes there. And then you got to figure out what's happening here. So to me, I would look at this as 2 to the 1st, 2 squared, 2 cubed, and 2 to the 4th. And those are in your denominator. And so it's 1 over 2 to the k. So that's how that works. That seems to be a good stopping point for this video. So that's the first 9 problems. Hope that helps.